Hello and welcome back to the videos for your linear algebra course. In this video we are going to be doing starting section 2.4, which is about shortest distances and closest points, and in particular we'll do section 2.4.1, the distance from a point to a line. So let's look at the goals for this section first of all, and the first of them is to determine the shortest distance between geometric objects in three-dimensional space, and the second is to determine the closest point on a line or a plane to a given point which is not on that line or plane. And so sometimes, this is just a little note, sometimes we'll just say distance, and when we say the distance between two objects will always mean the shortest or the minimum distance. And in Rn, so in particular in three-dimensional space, this is always going to be a perpendicular distance. So let's go ahead and start section 2.4.1. And so we're going to be given here a point A, like this one, and a line L, like this one. And we're going to do two things. We're going to find a formula for the minimum distance from A to L, which is going to be notated like this, the distance from A to L. So we're going to find a distance formula. And then secondly, we're also going to see how we might find a point Q, which is here. And that is going to be the point on L that is closest to our given point A, so our closest point. So we're going to do those two things. So let's start with the distance formula. So the first thing I'm going to do is remember that I can always see a point P on the line from the equation of the line, and I'm going to construct a vector from P to A. So that is PA. Now I'm going to add a little something extra to the diagram. I'm going to add some dotted lines to form a parallelogram. A parallelogram that has vectors PA and the direction vector D of the line as its sides. And if we look at that parallelogram, the height of that parallelogram, the height turns out to be exactly the distance that we want. So the distance from point A to line L is exactly the height of the parallelogram. Now, we know something about the area of a parallelogram. It's the base times the height. And in your unit on vectors, you had this formula. You had the area of a parallelogram is the norm of the cross product of vectors that make its sides. So the area is the norm of PA cross D. B, the base, we're going to take the base here as our vector D, but it's not the vector D, it is the length of D times the height. So the distance, the height that we're looking for, remember, which is the distance from A to L, is, well, all we have to do is divide. So the norm of PA cross D divided by the norm of D. So there is a lovely distance formula. If all we need to know is the distance from a point to a line, we can use this vector-based formula to calculate that. Now, if we want more than that, if we actually want to know this point Q, our closest point, well, we can start out the same way. We can start out by constructing a vector from the point that we can see on the line to point A, so vector PA. And now, if we take advantage of this right triangle, right, so if we do this, then the vector that I have drawn there in red, vector PQ, well, if we notice the geometry of that right triangle from what you did in your vector units as well, that is exactly the projection of vector PA onto the direction vector d. That's fantastic. So we can use that because we want to find q. So the position vector of q, so OQ, which will have as its components the same coordinates as point Q. That is OP, the point that we can see on the line, plus PQ. And PQ we just said is the projection vector. So OP plus the projection of PA onto D. So there is our procedure. We find the projection vector and we add it to the position vector of the point that we can see on the line. Now, a little something to note. If we have done this, so if we have point Q, then that actually lets us do the distance formula or calculate the distance in a different way. The distance from A to the line is the distance from point Q to A. And if I write that as a vector, well, that's vector QA. If I want the distance, then I'm talking about the norm of that vector. So the distance, if you have point Q, the distance can be calculated from A to the line as the norm of vector QA. And incidentally, vector QA in terms of our projection notation, that's just the orthogonal. That's the orthogonal component of PA relative to D. So if you have point Q already, you don't necessarily need to use the distance formula. You can use point Q to calculate the distance from A to L just as well.